Well, welcome back, everybody. This sequence, I'd like to introduce the concept of incidence. So let me first give you a roadmap of what we're going to be doing this week. I'm first going to give you a pretty overview of the concept of incidence, what actually incidence is, and then I'm going to talk about how we can measure incidence using two different techniques. First, I'll talk about measuring something called the cumulative incidence, and then in the following lecture, I'll talk about measuring incidence rates. After that, I'd like to explain the relationship between those two measures because they're both measuring something in common. So I'll talk about the relationship between cumulative incidence and incidence rates. And then I'm going to try to tie this sequence of lectures into what we talked about last time. Last time we talked about prevalence. So I want to talk about the relationship between incidence and prevalence. And then finally, I have a few problem sets that I'd like you to work with using the Framingham data set. So that's the roadmap. That's where we're going. But to begin, let's review what we talked about last time. Last time I started off by giving you my favorite definition of epidemiology, the definition that I learned as a student some 30 odd years ago. It says epidemiology is the study of the distribution and determinants of disease frequency in man. And just like last week, this week we will be focusing on the idea of distribution of, of disease. We're basically going to try to come up with a way to measure how much disease is going to be developing in a population that's being followed over time. But let's first review what we talked about last week. And what I'm going to use is that definition again and look at the first part of it that says we epidemiologists study the distribution of disease in populations. So what we do is we measure disease, we measure outcome. Last week we were measuring how much disease exists in a population at a point in time. We were looking at people in the Framingham Heart Study who attended the 1956 examination, and we were looking at among those people how many of them had pre-existing heart disease. What was the prevalence of coronary heart disease? So last week in the lectures and in the stated demo that Elizabeth ran, we were talking about the overall distribution of coronary heart disease and how it might vary in different subgroups of people, men versus women, smokers versus non-smokers. But this week I'd like to extend that now to look at another measure of disease frequency, a measure of how quickly disease is occurring in a population. New cases of disease are developing in a population when it's being followed over time. And that's going to involve this concept of incidence. We're going to be talking today in the future lectures about the incidence of coronary heart disease in the Framingham Heart Study. That was the main purpose of the study. They were interested in looking at people who were free of coronary heart disease when the study began, following them forwards in time, and measuring how many people developed coronary heart disease during that follow-up period. And in particular, they wanted to identify risk factors for developing coronary heart disease. They wanted to see if men develop heart disease more quickly, more commonly than women do, whether smokers develop heart disease more often than non-smokers, whether people with high blood pressure develop heart disease more often than people who don't have high blood pressure. So that's the topic we're going to be talking about this week, which is incidence. But first, let me give you an example of prevalence data, building on what we talked about last week. This table describes the prevalence of existing coronary heart disease at the 1956 examination, broken down by whether a person was a smoker or a non-smoker. This is a version of what Elizabeth showed you in the stated demo in the last sequence of lectures. Basically, what we have are 2,181 individuals who attended that 1956 examination. And at that 1956 examination, they were asked, has anyone told you, have you been previously diagnosed with coronary heart disease? And among the smokers, 86 of those 2,181 people answered yes. So we could measure the prevalence of coronary heart disease among the smokers at that 1956 exam. We could divide the 86 by the 2,281 and conclude that 4% of the smokers in the 1956 exam already had coronary heart disease. the prevalence of coronary heart disease among the smokers was 4%. Well, we could compare that to the non-smokers at that same examination. There were 2,253 non-smokers. Among them, 108 of them declared themselves of having pre-existing coronary heart disease. They developed coronary heart disease before that 1956 exam. We don't know whether they developed it the day before the exam, or 5 years before the exam, or 10 years before the exam. All we know is that when they were examined at the 1956 exam, 108 of those people said yes, they had been previously diagnosed with coronary heart disease. So what's the prevalence of heart disease among the non-smokers? It would be the 108 cases of pre-existing heart disease divided by the 2,253 non-smokers. The prevalence is 5%. And just as Elizabeth pointed out in her stated demo, notice that the prevalence is higher among the non-smokers than among the smokers. And as I mentioned in the last sequence of talks, we epidemiologists, whenever we see an association, we try to figure out the possible explanations, the possible reasons why one group of people might have more outcome, more disease than another. In this case, we're talking about pre-existing disease, prevalence of coronary heart disease. And as we talked about last time, there are 6 possible explanations I can think of for why the prevalence of coronary heart disease might be higher among the non-smokers. So what are the possible reasons why the prevalence of heart disease might be higher among non-smokers? Well, one possible reason is that prevalence depends on how much disease exists in a population at a point in time, and in turn that depends on how many cases of disease are happening in that population. Every case of coronary heart disease that existed at the 1956 exam had to happen before 1956. And maybe the non-smokers are a high-risk group. Maybe they have more cases of heart disease developing each year. So when I come along in 1956 and take a snapshot of those non-smokers and compare them to the snapshot of the smokers, one reason I'm seeing a higher prevalence of heart disease among the non-smokers is because non-smoking is a high-risk factor. Well, that notion that a group is at high risk for developing disease, the notion of developing disease is what incidence deals with, and that's what we're going to be talking about in this sequence of lectures. It may well be that the non-smokers have a higher incidence of developing new cases of heart disease. They are at higher risk. Well, that goes against everything we might think about. Everything we think about that smoking is a bad thing. We try to avoid it. Smoking, we expect, increases your risk of developing heart disease. So this first explanation is probably unlikely to be the reason why we're seeing the higher prevalence of heart disease among the non-smokers. Well, but there's other possible reasons. Another one is that since prevalence depends on how much disease exists in a population, it requires that people had to be diagnosed with heart disease in the past and still be alive in 1956 to be at that examination and answer, yes, I have been diagnosed with heart disease in the past. Maybe the non-smokers have heart disease that's milder than the smokers' heart disease. Maybe the non-smokers live with their heart disease longer. It has a longer duration of disease. And that's another reasonable explanation for why the prevalence in one subgroup of people might be higher than in another subgroup of people. The outcome in question, existing coronary heart disease, might have a longer duration among the non-smokers. Well, that is probably not likely also. Why would it be that if you developed a heart attack and you were a non-smoker, that heart attack would be less severe, you're more likely to survive it? Possibly, but maybe unlikely. But there are other possible explanations. The next one I suspect is the most reasonable explanation for that association we see in our data set. It's what Elizabeth and I referred to last time as reverse causation. Why are we seeing less heart disease among the cases of coronary heart among the smokers? Why is there less heart disease among the smokers? Well, rephrasing that, it's because there's less smoking among people who develop heart disease. You have a heart attack, your doctor says you have to stop smoking. So in 1956, all those people who had heart attacks in the past, have coronary heart disease. If they had smoked in the past, probably they're not smoking in 1956. So that reverse causation is probably the likeliest explanation for the association we see. But that's not enough. There's always at least three other plausible explanations for any associations we see in an epidemiologic study. Elizabeth mentioned these, I mentioned these. We always have to rule out, consider that the reason for an association has nothing to do with the factor smoking and the outcome coronary heart disease, but it's due to a bias in the study design, or it's due to confounding by other factors, or it's due to the role of statistical chance. All three of these topics will be discussed in more detail in this class. I'll be talking about the role of bias and confounding later in this course. Marcello will be talking more about the role of statistical chance. But this is the problem we're faced with when we have prevalent data. And this is the conclusion we might reach, is that whenever you report that the prevalence of disease is higher in one group than another group, you have this potential of multiple explanations. Now, why did the Framingham Heart Study get started in the first place? People wanted to know what are the risk factors for developing coronary heart disease. They were probably interested in knowing whether smoking is a risk factor for developing heart disease. And that is one of the plausible explanations for why you might see more heart disease among the smokers compared to the non-smokers, or in this case, the opposite was true. But if we're interested in identifying risk factors, the bottom line is that prevalence data, the data we just looked at in the previous example, is not going to be that useful. Because if I find an association between a potential risk factor like smoking and an outcome like prevalent CHD, I don't know whether the group with higher prevalence of CHD is because they're at high risk for developing coronary heart disease. That's what I'd like to say. Or it's a reflection of longer duration of disease with those people, or reverse causation, or bias, or confounding, or chance. So that's why prevalent data is not very useful for identifying risk factors for developing disease. We have to do something different. We have to measure something called incidence. We have to measure how many new cases of disease develop in a population that's being followed over time. So back when the Framingham Heart Study started, they wanted to enroll people who were free of coronary heart disease. If you showed up at the baseline examination and already had coronary heart disease diagnosed previously to that baseline examination, you're no longer at risk for developing heart disease for the first time. You already have it. So they probably told those people, thanks for coming, but you're not very useful for us because we want to answer the question, does smoking increase the risk of developing coronary heart disease? They wanted to measure incidence, and that's what we'll be talking about in this sequence of talks. So let me first just describe the concept of incidence. What it's trying to measure is the development, not the existence of disease at one point in time, but the development of disease in a population that's being followed over time. Now that population that you're following over time to observe all these new cases of heart disease that develop, we refer to that as the population at risk. Now to be at risk for developing heart disease for the very first time, you have to be alive and breathing, and you also have to be free of coronary heart disease at the beginning of the study. So depending on the outcome you're going to be measuring, and I'm talking about developing the new cases or observing new cases of coronary heart disease that develop, you want to enroll a population and follow them over time. You want to enroll a population that's at risk for developing heart disease. And if you're interested in developing heart disease for the very first time, that means what you want are people who are free of disease at the beginning of the study. They have not had coronary heart disease diagnosed with them yet. Anybody who has coronary heart disease diagnosed at the beginning of our study is not going to be useful for answering the question, what's the incidence? What's the risk of developing coronary heart disease during a period of follow-up? They're very useful if you want to answer a different question. Given that you've already been diagnosed with heart disease, what's your chance of having a second, say, heart attack? Well, to be at risk for a second heart attack, by definition, you have to have a first heart attack. So if I had a different research question identifying risk factors for developing a second heart attack among people who had survived their first heart attack, then I want my population at risk to be people who had previously been diagnosed with a heart attack and are alive and kicking. So that's the notion. We start out with a population at risk. We follow it over time. And we observe who develops the disease, coronary heart disease in our example, and who doesn't. Now, how are we going to measure the occurrence, the development of coronary heart disease? Well, in future lectures, we'll be talking about two commonly used measures. One is called the cumulative incidence. Sometimes that cumulative incidence is referred to as an estimated risk. Sometimes it's referred to as an average risk. What it's going to be is a proportion. And remember, Marcello in his lectures talked about probabilities being based on proportions. So since it's a proportion of people who develop a disease, it can be used as an estimate for people's risks of developing disease. That's why it's sometimes referred to as an estimated risk. And if you have different people with different actual risks, what you're getting is essentially an average of all those different risks. So it's sometimes referred to as an average risk, but we're going to be calling it a cumulative incidence. It's going to be calculated, as you see in a future lecture, by essentially counting the number of new cases of disease that occur when a population is followed over time and dividing that by the size of that population at risk. And I'll give you an example of data that we'll be using to drive this notion home in a minute. But later I'm going to talk about a second measure of incidence, something called an incidence rate, which has the same numerator, number of new cases of disease that developed in this population as it's followed over time, but has a different point of reference. Instead of comparing it to the number of people you start with, you compare it to how much person time you observe in that study. Person time is the notion of observing a person over time. In the Framingham Heart Study, they initially enrolled around 5,000 people. They planned to follow them for 20 years. So essentially you can consider each person as a separate timeline, starting in around 1950 when the Framingham Heart Study began, and going forward in time until they either developed a disease or they were lost to follow-up or some other event ended their follow-up. And I'll show you what I mean by person time and the notion of it being a timeline in an example that I'll show you right now. So let's suppose I chose 100 of you by random. And on the very first day, what I decided to do was I was going to send you an email, or better, call you up at home at the end of the day and ask, have you developed a headache during this day? And let's suppose, to make life simple, let's suppose these headaches happened at the very end of the day. And what this table is supposed to show is the occurrence of headaches among 100 typical students in this class if they were followed over a 1 week, a 7-day period. So for example, person number 1, on the very first day, person number 1 develops a headache. Person number 2 develops a headache on that same first day. Person number 3 and person number 4 also develop a headache on the first day. So 4 of the 100 people develop headaches on their first day of this class. Person number 5 develops it on day 2. Person numbers 6, 7, and 8 develop it on day 3. Persons number 9 and 10 develop it on day 4. Another person develops it on day 5. Two other people develop it on day 6. And one other person develops it on day 7. And everybody else never develops a headache. Every time I call them up at the end of the day and ask, have you developed a headache today? They answer no. So where you see these X's represents that when they were called, they answered no. And I was only interested in the development of a first headache. So once you develop a headache, the first headache, you are no longer at risk for developing a first headache. You're no longer going to be followed. You develop the outcome. I don't care if you develop another headache 2 days later. I'm not interested in second headaches. I'm only interested in first headaches, and you're no longer at risk for developing a first headache once you develop such an event, once you develop such a headache. So what's in this last column over here is the amount of time each person was followed until they developed a headache. 1 day for the first 4 people, 2 days for the next person, 3 days for the next 4 people, etc. Or 7 days, meaning for those who never developed a headache, they answered no, 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 no headaches for 7 days. They were followed for 7 days. Their follow-up time is 7 days, and the study ended. Now, you could display this same data in terms of timelines, and that's what this next figure is supposed to describe. Each of these arrows is a person. The length of the arrows is the number of days they were followed until either they developed a headache or, in this case, the study ended. So the first 4 people's arrows only go for 1 day, and they end with the development of the disease. The development D means you developed a headache. The next person's line went for 2 days, and then it ended with him developing a headache. And everybody down below, like for the 100th person in the study, they were followed for 7 days. At the end of the follow-up, there's nothing there. That means the study ended. So what we have in this last column, again, is the same follow-up time. Follow-up time either until they developed a headache or until the study ended. Well, here's what I'd like you to do. I'd like you to look at either of those 2 previous slides, the table with the X's and the D's, or the table with the lines ending with D's. They're the same information. And answer the question, how would you quantify the incidence, the development of headaches in this population, in this particular study? And in the next lecture, I'll give you one possible option for quantifying how much headaches are developing in this study. In the following lecture, I'll give you the alternative way we could do it. So think about this for a while. Come up with what you think is your best way to describe the incidence of headache development. And then we'll talk about that in the next section. So I'll see you then.